Let's look at a basic sensor interface like this one. We'll cover this in more detail in a later video. For now, just notice that you have some sort of low-frequency sensor that we run into an RC filter to reduce the amount of noise that's present at port 0 bit 2, amplified it by a gain of 24 with an offset provided by the DAC, and this will be explained why you might want to do this later. The output of the PGA goes to a SAR, Successive Approximation ADC, Analog to Digital Converter. How would you go about debugging this? Well, you might think, well, I'll just use the debugger that's built into PSOC. And while that's a very useful and powerful tool, it doesn't have all the features that you need to figure out if this input circuit is actually working. The debugger really only works with code, and we need to see the signal before it hits the SAR ADC. That's where an oscilloscope comes into play. Some of you will be lucky enough to have an oscilloscope already. For the rest of you, there is the Nscope, which is a very low-cost 4-channel digital oscilloscope with signal generator and pulse generator and power supply all built on one little board. Of course, it is not as fast or as high resolution as a much more expensive benchtop oscilloscope, like this one from Tektronix. It's super fast, has multiple channels, it has color, it has digital inputs. It's just an amazing piece of equipment. But it also is too expensive for most of us to buy. So we'll tailor the exercises in this course to work with the limitations of the Nscope so that you get a view of what the signal looks like before it gets digitized. For example, in this basic sensor interface, you could look at the low-frequency sensor with noise before and after the RC filter, and you could see how much of the signal and how much of the noise has been reduced by that filter. This is not something you can get from PSOC's debugger because the signal hasn't even appeared to the microprocessor until it gets through that ADC on the right side. More information is available if you simply hook an analog output pin to the PGA's output. You could then connect the Nscope to P01 and see if the amplifier is doing its job. The Nscope connects to your PC using a standard micro USB cable. Once you download the software that goes with it from the Nscope site, it will look like this on your PC. The first thing to look for is that power indication in the upper right. If everything is okay, you will see USB power and a little bit of a green bar there indicating that the device is drawing power from the USB input and providing it on its plus and minus 5 volt rails. There are 4 channels here, channel 1, 2, 3, and 4, so it's a 4-channel color digital oscilloscope, which is pretty cool. You can turn the channels on and off just simply by clicking on those buttons, and there's channel 1. Notice it is color-coded. Channel 1 is red, or it's 1 volt per division. This scope works with slider bars, unlike most scopes which work with knobs, but it's easy to use. I have connected a wire from the analog signal generator here, A1. I connected a wire over to C1. So if I turn on A1, we immediately see a sine wave. Notice I've selected sine wave here. It's 4 volts in amplitude, and it looks like that's 4 volts peak to peak, although they did not specify it. I can easily change the frequency here and make it go much faster, so fast that it blurs. And in order to spread that out, I've got a horizontal control over here. Time per division, which is currently 500 milliseconds per division. That's the time from one vertical line to the next vertical line is half a second. I can slide that over and make this go quite a bit faster. And there's the sine wave again, but notice it's jumping around because the Nscope is starting to collect data randomly relative to the signal generator, and that's where trigger comes in. Most of you should know how to operate an oscilloscope, but if you don't, here's a quick lesson. In this case, I will turn the trigger on, and that tells the Nscope that it wants to look for a rising edge on whichever channel is selected, and none is selected here. So I'll click on channel 1, and as soon as I do that, we see this white dotted horizontal line that says trigger. And it's currently sitting there at about 0 volts. I should probably line that up. There it is. Line that up with the major division. Since our signal is going from 0 to 4 volts, we don't see a rising edge on channel 1 that goes past 0 volts. It just goes down to 0 volts and just grazes it, or maybe is a little bit offset. In order to change that voltage level, I left click and drag on the trigger here, and when I let go, suddenly we see the signal reappear. There's a vertical dotted line, and that tells us the time at which the Nscope is starting to collect data based on this trigger criteria. A rising edge on channel 1 past this voltage level, and there it is. And so now the signal is stabilized because the time at which the Nscope collects data is synchronized to the time at which the signal generator produces the sine wave. You can do all sorts of flexible things here. For instance, I could turn it from a sine wave into a triangle wave just with a press of a button. I can make the signal smaller or larger up to some limit. I can also slow it down or speed it up. If we look over here on the horizontal scale, the time scale of 1 millisecond per division is not terribly fast. If I scroll to the right, the fastest I can go is 10 microseconds per division. And I think I said in a previous video that this thing samples at 10 kilosamples per second, and that might be wrong. I think it samples faster, but the fastest you can display the oscilloscope is 10 microseconds per division. Compare that to a benchtop oscilloscope from a company like Tektronix that costs in the neighborhood of $10,000, and it can go thousands or millions of times faster than that. In addition to the signal generator, and we have 2 of those, there are also pulse generators, which just basically produce square waves, and they work the same as the analog outputs. Notice that the Nscope does not have any features like being able to do a fast Fourier transform or different types of persistence modes and so on. Despite that, it's a very useful and powerful tool, and it adds a lot to the debug capability that we have in this lab.